Hello everyone, and welcome to Elec 3310, Advanced Microcontroller Systems. We're in Chapter 7. This is the online version. And what we're going to talk about here is understanding the function of a digital output, and that's the digital write function, and the analog output, which is analog write. So, if we want to review just digital output on the Arduino board, all the digital pins can be used for I/O, input and output. A digital output on the Arduino is around 5 volts, and or it could be a 0 volts. So a high would be 5 volts, a low would be 0 volts. So if we use digital write, we have to use this syntax. The output pin, and we can say high, or we could say the output pin and low with the digital write. So that'll turn something on or off depending on if it requires a high or low. But before we use this on a digital write, this is the one thing that's different. You have to use the pin mode output pin to set it as an output. So it'd be dedicated as an output when you use this. If you need more details, go to the reference, the Arduino reference. So an analog output is another function, and we can use the digital pins for an analog output, but they only occur where the squiggly line is etched on the board. For the Uno, that's these pins, 3, 5, 6, 9, 10, 11. Now if you're using the Mega, you can go through pins 2 through 13. There's a lot more there. And really the analog write is not really a true analog signal. But make sure you understand the syntax for analog write. We don't have to set it as an output like we do the digital write, but we have to specify the pin and the value. And that value is going to be a number between 0, which is always off, and 255, which is always on. So this is what the pulse width modulation looks like that comes out of an analog write when you're given a value between 0 and 255. So you're actually varying the duty cycle with that value number. So here you have analog write pin 0 and it's always off. And if you have an analog write and you have the pin number in 63, you have a 25% duty cycle. And an analog write pin number and then that 127 value that you put in there gives you a 50% duty cycle, and so on. And 255 is always on. So you can vary the duty cycle of your pulse width modulation using the pins, using analog write. So this chapter deals a lot with cool technologies for visual display. And let's make sure we understand something fully, something we use a lot, and maybe we don't give it a lot of thought. And if you're designing boards professionally, you'll need to do that. And one thing to think about, like say the red LED, we use that a lot. Now other colors will have different values than that, but it requires about 1.8 volts to get that thing to light up. And the continuous current that we can run through that would be 25 milliamps. But if we pulse it like we saw earlier with those different duty cycles, we can pulse it, we can go a higher current of 160 milliamps. So we can control the brightness of the LED. So we always use resistors with the LEDs, but do we actually determine the value through some kind of scientific effort that we do? Sometimes we don't. So it all depends on the amount of current we want to allow to flow through the device. This will affect the brightness. And let's go through this example. So if we want to limit the current to 15 milliamps, here's a formula we could use. The voltage from the source minus the forward voltage of the LED, which in the red has a certain value, 1.8 volts. And if we're using 5 volts for our source voltage, and if we want 15 milliamps to go through there, then we'll limit it to around 213 ohms. So we have to find something that's close to that, and 220 might be one we could use. If we want it brighter, it'd be less resistance, and that would be 160 ohms. So that's a couple ideas right there. Now, we could run through this program, but there's a lot of comments that on practically each line that'll explain the code. But what I'd like to draw attention to you is, I'd like you to look at the function call. So here's the function right here, and here's the function call. So you can use this to you can use function calls to make your program easier to follow. And really that's the way professionals do it. And so this would be a nice example for us to start using to create function calls and make our code easier to follow. Look at the anatomy of a function call in the C language. So if I read here the functions here, the segmenting code into functions allows a programmer to create modular pieces of code that perform a defined task and then return to the area of code from which the function was called. So it'll come down here and do this work and then go back to where it was called. And it makes it easier to stay organized and for others to read your code and to follow it if they have to make changes to it. So if we look at this one here, we're taking integer values x and y, and then basically what it does is it multiplies it, puts it in a value called result, and it returns that as an integer back to the program, so it comes back with a value. Now if you're not going to return anything, you just put void there. So a lot of times you'll see programs with void and you ever wonder why it's there, because you're not returning anything. So earlier, the program that I showed you with all the comments on slide 7, and that was really sketch 7.1 in your book, it used digital write to control the LEDs. If you kept the same hardware laid out the way we had it on that program, 7.1, and we run 7.2, this time we're going to use it using pulse width modulation to control the LEDs, and that's using analog write. And that's how you produce pulse width modulations. So you should be able to run this and be able to walk through this with all the comments and understand that code. Now, I just want to review a discussion of tools that we use for decision making. And one tool here is the if-else statements. So when a true test is encountered, that code will be executed. Notice the abundant use of brackets for each test. And only the one that's true is going to be executed. A special tool that could be used also is the Switchbreak statement tool. If I look at these last two bullets here, a switch statement compares the value of a variable to the value specified in case statements. And when a case statement is found whose value matches that of the variable in the code, that case statement's run. It's just like the if statements. There's another word that we have to use in there, break. It's a keyword that exits the switch statement. It's typically used at the end of each case. The switch statement will continue executing until it sees that break. So it's very important to have that in there. So here is a snippet of code that shows you how a switch break function works. This is similar to the if statements, and it specifies code to be executed for various conditions. It's just part of the decision-making tool set that we have. So we see here case 1 will do that. If that variable equals 1, and then it'll break. If it's not true, it'll look at this one. It'll do this one when it equals 2, and so forth. And then there's a default here that will run no matter what. So for our work at home, I'd like you to run those sketches 7.1, 7.2, and also 7.4, 7.5, and 7.10. They're all in Chapter 7 of our textbook. And develop a program to count 0 through 9. It would be nice if you used a function call. And what we're going to do here is count 0 to 9 on a 7-segment display. And we've used that before in our first class, the microcontroller class that we did earlier. And so this shouldn't be anything new for you. You should have this done and provide a sketch of your circuit diagram. Have this done by April 1. That'd be the time of our next class after this week. And let's look here. This is a common anode 7-segment display, and we've run this before. We know about this. You could run program 710, and if you have a common anode at home, and you could use 220 ohm resistors between each of the pins to each segment that we have here, and that would light it up consistently. And so don't forget the anode is the positive side of the LED, and the cathode's the negative side, or the cat whisker side. So you want to use a value of all the same values so to get you a continuous even lighting of that. So that's until the next time. Be safe and help somebody in need. Thanks. Have a good evening. Bye-bye.